By the end of this lesson, you'll be able to describe how the value of the leading coefficient affects the graph of the quadratic function. You'll be able to use your calculator and a table of values to draw conclusions about what you see. The Do Now asks for you to complete the tables for each function and then graph and label each function on the coordinate plane. You can see that the parent function, y equals x squared, was already given to us with a full table. So this parent function for all quadratics has already been graphed. I plotted from -3 up 9, -2 up 4, -1 up 1, and so on. Right now, I'd like you to take some time to pause the video and create a graph for each of the other functions. Remember, you can go into y equals on your calculator, clear out any old function, and type in the one that you're asked to find. And then when you hit second graph, you will get the table. This table begins at -3, so my table should begin at -3. I will copy these values into the table and then plot them accordingly. As you plot, after you're done connecting your curve, remember to label each function as well. Please pause the video here and complete your graphs. Okay, as you can see, I filled in my table and graphed y equals 2x squared here. Make sure you label it, especially because you might not be using different colors. And now let's check out our table and graph for y equals 1/2 x squared. And here you see the graph and table for y equals 1/2 x squared. Every single graph has some similarities with each other and the parent function, and then each of them have a difference from the parent function. It says, describe the effect of the leading coefficient on the y values in the table. Well, the leading coefficient is referring to the a value. So if a is 2, it appears that this graph stretches super tall and each of the y values are double the original from the parent function. If you notice, the parent function was 9, it doubled to 18, 4 doubled to 8, 1 doubled to 2, and so on. Each of these values, y values, have doubled. However, when the a value is 1/2, 9 did not double. This time it cut in half. 4 cut in half to 2, 1 cut in half to 0.5, and so on. It is consistent throughout the table. So the y values either increased when they doubled or decreased, got cut in half. Okay, now we're being asked, how does the graph of y equals 2x squared, this is our red graph, the second table, change the graph of the parent function? So this red graph, there are many things that you can probably see. The graph is taller, it's narrower, its slope increases, it has a steeper slope, and we can call this a vertical stretch. It stretches out vertically. Remember, vertically goes up and down, so it stretches out, up and down. We are then asked, how does the graph of y equals 1/2 x change from the graph of the parent function? Well, if the parent function's here in blue in the center, now the green function is shorter, it's wider. The y values, we said before, cut in half. So the graph of 1/2 x squared is shorter and wider. The slope decreases. It does not have such a steep slope, such as the blue one in the middle, or especially compared to the red one. And we can call this a vertical shrink. Vertically, going up and down, it's shrunk. It's not reaching as high at the same time. If this was to represent time, 1, 2, 3 seconds later, the parent function reaches here at 9. The red function reaches twice as high, but this one is only half as high as the parent function, indicating a less steep slope. Now we are asked to calculate the rate of change of each of these functions over this interval from 0 until 3. These should be closed intervals. Okay, so rate of change, you should be thinking of slope, which means you should be thinking of m, which also means you should be thinking of this formula you should have memorized, because it is not on the reference table for the regents, But anytime you ask for rate of change, we want the slope, and that can easily calculated by using a table of values. It wants us to calculate the slope for each one, so let's start with the parent function from 0 until 3. So this would be our x1, y1 value, and these would be our x2, y2 values. So if I plug into the formula, y2 is 9 minus y1 is 0 over x2, which is 3, minus x1, which is 0. So I end up with an m value of 9 over 3, or 3 over 1. This would be my rate of change. It increases 3 units for every 1 unit over. Okay, now let's find the rate of change for our second function. Y equals 2x squared. We'll have an x1, y1 of 0, 0, and an x2, y2 value of 318. y2 minus y1 over x2 minus x1 will give us a slope of 18 over 3, which simplifies to 6 over 1. Its slope increases 6 units for every 1 unit across. And we've already noticed that before. We agreed that this is a much steeper slope in comparison to the parent function. And last, let's find the slope of our y equals 1/2 x squared function. I have x1 and y1, x2 and y2, y2 minus y1 over x2 minus x1. We end up with y equals 4.5 over 3. So we have a slope of 1.5 over 1, or 3 over 2. And as we can see, this is definitely the least steep of a slope. I'm only increasing 1.5 boxes for every 1 box over in comparison to 6 or 3. To summarize all of these changes, we can look at this standard format that is very similar to what we've seen so far when talking about our vertex and completing the square. HK still represents our vertex. The sign of A, meaning whether A is positive or negative, describes how the parabola opens, its end behavior. When we have a positive A value, it's going to open upward. And when we have a negative A value, it will open downward, which is what we see here. So positive A is upward, negative A is downward. Negative A is actually indicating that there is a reflection in the x-axis. Now the actual value of A will tell us how steep the slope or rate of change is. When A is a number larger than 1, like the red function we saw before when A was 2, a number larger than 1, it increases the slope, causing the parabola to get tall and narrow. When A is between 0 and 1, meaning a fraction or decimal, the graph will show a decrease in slope. It will become a shorter parabola and wider. Please be sure to bring these notes with you to class tomorrow so that you can use this key here to help you describe certain transformations. We now know how the leading coefficient affects the graph of a quadratic function, and we can see that just by testing values in our calculator and graphing them, we can draw some conclusions based on what we see on our graph, or if we specifically calculate rates of change. Thank you for watching.